In order to start by something, I have measured the resistances between some pins of these three connectors. And one connector is interesting, it's P1, this one. So this is a quick pinout of the connector. There are two things actually. So there is one common point, which is pin 12 here, and between this pin and four other pins, there is a resistance of 17 ohms. This is something like that, pin 12, and pin 1, 11, 10, and 9, there is a resistance of 17 ohms. And there is something approximately equivalent between these 5 pins. There is also one common point, and there is a resistance of 60 ohms between this common point, which is, I don't remember which one. You can see that between this point and this one, this one, this one, and this one, there is a resistance of 60 ohms. So this should be a sensor, probably, and these 4 coils should be actuators. So I have tried to apply a DC voltage between this point and the 4 others, and effectively this provides a movement of the sensor head. Let's have a look. Okay. And I will apply the positive voltage to that point. There is a power supply of 10 volts limited to 0.4 amp. Okay. So you can see it is possible to move actually the head in all directions. So I think that these coils are the precession coils of the gyro, and I made also some measurements, and these coils are connected to that board here, actually to the collectors of these 4 transistors. So that board has something to do with the position of the sensor. The next step will be to do the reverse engineering of that board. It is not very complicated. I think I will need one complete day for that task. Okay, I have done the complete reverse engineering of that board. There are 2 pages for the schematic diagram. The first one is here. So this board permits effectively to drive the precession coils of the gyro. It permits to orientate the optical sensor to a given direction. There are 2 identical circuits, one on the top for one axis and one on the bottom for the second axis. So I will describe only one axis, and the second channel is absolutely identical. So you can see that there are 2 inputs. One here is external and one is internal, depending on the state of this signal. I called cell here. So the precision coils are driven either by the internal circuit, and this is actually a servo control, or externally. So there is one signal here for one axis and the second one for another axis. These signals are connected to the connector here. We can see that one signal is inverted using this op-amp used as a comparator. There is a diode in the feedback, so this permits to have a negative voltage of minus 0.7 volt and a positive one which goes to the power supply. On the right there is a power stage, so this is actually a current source. You can see the resistor here. The current is defined by the voltage here. When the output of the comparator, this one for example, is at high level, this diode is reverse biased and there is a voltage across this resistor which depends on the values of these resistors and the voltage V1 here. So this voltage permits to have a current which flows through the resistor here and through one of the precession coils. If one input here is at high level, the second one is at low level, and vice versa. So when the voltage is at low level, that is to say minus 0.7 volt, so there is a voltage of 0 and there is no current flowing through the precession coil. On the left, we have 2 inputs here. These inputs are connected to the head. The middle point is connected to the ground actually. We can see also that the two other pins here are connected to an AC power supply through the resistors of 5K6 here. Even if we don't have access to the internal stuff of the head, this is probably a differential inductive position sensor. We should have a moving core here. When the core is centered, there is the same impedance on the top coil and the bottom coil. So this permits to have the same amplitude at this point and at this point. In that case, the DC voltage in the middle point is 0. If the core is not centered, there is an imbalance of the AC voltages here, and this permits to have a positive or a negative voltage at that point. So obviously this thing permits to have a reference position of the head. So this is a kind of home position. I don't know if there is a specific terminology for that. So when the cell signal here is at low level, the information here permits to drive the precession coil. In that case, the optical sensor is centered. This is the servo control loop, and it is the same for the second channel. So now let's see the second page. This is the rest of the schematic of that board. There are three different things. Let's start with the simple things. You can see on the bottom left here a voltage follower. This permits to drive the logic voltage of the analog switches. So we can see something interesting. Normally this voltage is about 5 volts. You can see that we have a divider with a ratio of 2. So that means that the power supply should be around 15 volts. We can see here a VIN oscillator, so this permits to generate the voltage for the inductive sensor we have seen. These voltages here, this one, and this one, and this one, so this permits the excitation of the inductive sensor. So this is the classic VIN oscillator. So it uses also two diodes here, which permits to have a non-linear gain. So this permits to stabilize the amplitude. So this is a very simple thing. So I have calculated the frequency according to these values. So this gives a theoretical frequency of 32 kHz approximately. And on the top, there is something quite interesting. So we can see that there is one input here. So the input A actually is connected to that line here. This is the output of the first comparator, this signal here. So this is a logic signal, which should be a square signal. This signal is fed to this monostable. So this is an accurate monostable. So it is not complicated. In idle state, the output here is at high level. This capacitor is charged to the power supply plus V across this resistor and this diode. So the voltage across this capacitor is approximately plus V, minus 0.7 volts. The output is at low level because the voltage here on the negative input is higher than the voltage of the positive input, which is connected to ground. There is 0.7 volt here. The output is minus 15 volts approximately. So this transistor is open. Okay, so there is a steady state with plus 15 volts here, 0.7 volt here, and minus 15 volts at the output here. So now if you suppose that you apply a negative voltage here of minus 15 volts, in that case the voltage here will be approximately at 0 volt because this resistor is connected to plus 15 volts, so there will be a voltage close to 0 here. But as the capacitor was charged at plus V, in that case, the voltage at that point will be minus V. So at the output, there will be a high level which will turn on this transistor, and this will set this voltage at 0 volt. And this voltage will evaluate from minus V to plus V across these two resistors in series. At one moment, the voltage will cross 0 volt at that point, and the output will go to low level, and this will turn off this transistor, and this will be in steady state. So at the output, there is a positive pulse with a duration of 0.7 times the time constant here. I have calculated the duration here of 7.22 milliseconds approximately. And you can see also something interesting, that there are two resistors in series, and if you calculate the sum, it gives a value of 107 kilo ohms. It is strange because this value is normalized in the E96 series. So I think that this value is measured during production, and this resistor is added according to the capacitor in order to have a given pulse duration, but I'm not sure. So we can see here something interesting, that the signal at the output is filtered using this time constant here, this resistor and this capacitor, and is compared to a value, and this gives the output And at the output of the comparator, there is a voltage divider in order to give a voltage of 5 volts. And this voltage actually is a selection voltage, which permits to select between the servo control, here when the signal is at 0, and the external command when the signal is at high level. So we can see that there is something interesting, that is to say that at that input we should have a square signal with a variable frequency, and for a given frequency, which corresponds to a period equals to 2 times the pulse duration, that is to say something like 14.4 milliseconds, there is a change of the selection here. So I don't know exactly the purpose of that thing. I have calculated it corresponds actually to an input frequency of 70 Hz or something like that. So this is maybe a detection of the final velocity of the gyro. So in that case, maybe there is a coupling between the gyro and also these coils. So this permits maybe effectively to select the output precession signals when the gyro is fully operative. And in that case, probably that this sensor is used when the gyro is not operative. In that case, there is a centering of the sensor head. So we can see also another thing, which is the signal V1. So the signal V1 is here. So this permits to set the current which flows through the precession coils. So we can see that there is a second order filter. So this seems to be a strong filter, which is connected to the output here. So we can see that when the duty cycle is 50%, so this value will be close to 0. And when this voltage is 0, the current flowing through the precession coils are close to 0 also. So this permits to increase the stability of the control. I have found that the power supplies of that board are connected to that unit. So this is effectively the power supply unit for that system. I have found the pinout for some power supplies. This is plus V for the power supply and minus V. This is also the power supply for the precession coils. So this power supply doesn't need to be regulated, so I think this is also the power supply input of the power supply itself. And I have found also another board, the pin for the plus 5 volts. So the result is here. This is a 15 pins sub-D connector. So there are several grounds. So pin 5 is the positive power supply, and there is a power voltage for the precession coils, which would be also, in my opinion, the power supply input. 2 pins are connected together and connected to the plus 5 volts. So there are probably other power supplies which are used on that system, but not for that board here. So what we can do is to connect an input power supply of 28 volts, for example, between the power input here, pin 4 and pin 6, which correspond to these pins. So the positive power supply here, and the negative one, which is connected also to the general ground. Okay, so I have connected the pins 4, which is the input power supply normally, 7, 10, here, and 14 to the ground. Okay, so this is the ground, and I will connect the input power supply, I suppose to be pin V power, pin 6. There is also a second one, pin 13. I will use only pin 6. Okay, I will set the power supply to 20 volts, for example. Okay, I will set the range into range. Okay, so let's start. I am going to turn on the power supply. Okay, so you cannot see, but there is a current of 420 milliamps at 20 volts. Okay, so let's see, for example, if we find the negative power supply on pin 3. Pin 3 is here. Oh, look at that, we have minus 16 volts. Let's see the positive power supply, plus V, which is connected normally to pin 5. This one, plus 16.7. And this is a good start. Let's see the plus 5, pin 11 and 12. Look at that, 5 volts. Okay, so this thing works. So let's see the other pins. Pin 1, for example. So pin 1 is here. Oh, look at that. You have minus 243 volts. Well, this is dangerous. So this is used maybe to charge the capacitor in order to have the ignition of the explosive. Minus 244. Okay. So let's see pin 2. Minus 25.7. 25.7. So pin 3 is minus V. Minus 16. So it is closed to the minus 15 volts I have estimated. So pin 4 is a ground. Pin 5 is plus V, which is 16.75. Pin 6 is the power input. 7 the ground. Pin 8. Okay, there is also a minus 5 volts. Pin 9. Minus 12 also. So pin 11 and 12. This is the plus 5. And pin 15. Seems not connected. So this is the complete pin out of the power supply. So there is a voltage of minus 244, minus 26, minus plus and minus 16, minus 5, plus 5, and minus 12 volts. Okay, I have connected this unit to a power supply. So let's turn on the power supply. Okay, you can see that the sensor keeps its position, and you can hear also the precision coils. Okay, the gyro is rigid, but the precision coils readjust the position every time. we can do some measurements. So first we can have a look at the output of this oscillator, this point here. The frequency of this signal is 30 kHz. So it is close to the theoretical value of 32 kHz. Maximum voltage is approximately 13 volts. The second interesting signal is this one. So we should have here a rectangular signal. It can be interesting also to visualize at the same time this voltage at the input of the comparator. Okay, so for the last measurements, I have connected the first channel of the oscilloscope in yellow here at this output, and I have connected the second channel in green to this input of this op-amp. So we should have a DC signal starting from a negative value and increasing slowly up to 0 volt or something like that. So we can check the duration of the pulse width here. There is a duty cycle close to 50%. Okay, so let's start. Okay, so we can see that there is a negative voltage which increases with time. And we can see that there is also effectively a frequency which increases with time. Okay, so we can see that there is a pulse of 7 milliseconds. So this is close to 7.22 milliseconds I have calculated. And we can see that there is a duty cycle also, which is exactly 49%. So this permits effectively the detection of the final velocity of the gyro. We can see also that the voltage at the input of the comparator is between minus 500 millivolts and 0 volt. So actually this voltage here is above the threshold, which is minus 1 volt. So there is effectively a high level at this output. So that's all for today. Next time I will try to do another reverse engineering of another board. Thanks for watching and see you next time. Bye bye.